Let me keep going then. Okay. All right, so now we had exponents. Let's now consider negative exponents. So for any non-zero number a, okay, for any non-zero number a and positive integer n, right? For any non-zero number a and positive integer n, we can consider a to the negative n. So we're negating the exponent. This is equal to 1 over a to the n. This is equal to 1 over a to the n. That's what this is equal to. So when you have a to the negative n, when you have a negative exponent, you do 1 over is what this is saying. Or you flip it, in other words. When you have a negative exponent, you flip. You do 1 over. So a to the negative n is 1 over a to the n. And you can hopefully you can see why a has to be non-zero, mostly because if a were 0, then this could be 0, the denominator. So basically we're avoiding dividing by 0. You know, you never divide by 0. And what's a nice consequence of this and some other exponent rules is that a to the 0 is 1. A to the 0 is 1. I'm actually going to show you why this is true. I'll give a sketch of a proof as to why this is true. Again, this is when a is not 0. So here are some examples. 2 to the negative 2, right? Well, that's going to be 1 over 2 to the 2, or 2 squared, which is 1 over 4. Negative exponent, 1 over. Or flip, in other words. 3 to the negative 5, 1 over 3 to the 5, which is 1 over this. This I actually used the calculator for. 3 to the 5th I did not do in my head. So, So that's what negative exponents. Okay, so we said a had to be non-zero here. Well, what about when we have 0? Well, 0 to the n, right? That's going to be just 0 when n is a positive integer, for any positive integer n. And why is that? Well, here you're just multiplying 0 with with itself n times. So you have n copies of 0 and you're multiplying them together. You know, but 0 times anything is 0, so we get 0. When the exponent's negative, that's 0 to the negative n, in other words, is not defined. So you don't raise 0 to a negative exponent. That's just not defined. Again, because you can't divide by 0. 0 to the 0, that's also not defined. I know it's tempting to write this as 1, but it's not defined. It's just, you know, nonsense. Yeah, I guess I'll say it. It's nonsense in this course, so to say. Okay, that's good. So we have that case. Okay, so we had negative exponents. Well, we have this rule with product and exponents. Let's see what happens then. Okay, well, let's consider an example. Let's suppose a is any real number. What real number is it? I don't know, but who cares? If we do a cubed times a squared, a cubed times a squared, right? Well, okay, what is this equal to? Well, here we're multiplying a by itself 3 times. Oh, excuse me, we're doing 3 copies of a and we're multiplying them together. A squared, we're doing 2 copies of a, right? And we're multiplying them together. Now, one of the nice properties about multiplication is that it's associative. So we can actually use parentheses any way we want here, since we're just multiplying. Okay, well, if we take those parentheses away, we end up with this. And again, we can take the parentheses away by associativity. We have 5 copies of a, though, which is a to the 5th. So we get a to the 5th. And of course, that's equal to, and 5 we know is 3 plus 2. So when the dust settles, we get a cubed times a squared. That's going to be a to the 3 plus 2. So what am I saying here? We multiplied, and we end up adding the exponents. And that's really the next rule here. If a is a real number, m and n are integers, a to the m times a to the n, that's a to the m plus n. So when you multiply like bases, you add the exponents. When you multiply like bases, you add the exponents. And these are just examples illustrating that. So 5 to the 4 times 5 squared, right? Well, here that's just, here we're just doing 5 to the 4 plus 2. We're just adding the exponents. That's all I'm illustrating. Same thing over here with the 8. 8 to the 5th times 8 to the 7th. Well, that's 8 to the 5 plus 7, 8 to the 12th. Yeah, I don't know what these numbers actually turn out to be, but that's what I guess we can use a calculator for. Well, this number, I would imagine, is pretty big. This convention, this is actually a convention that the book is making. When you have an equation like this, we're assuming that both sides exist. That's what we're assuming. I mean, if a were positive, then m and n, right, really could be, I guess, anything we want, any kind of integer. But remember, if m and n were negative, then a would have to also be non-zero. So in order to avoid writing all these cases and to avoid, I guess, excessive writing, this is the convention that the authors are making. I really hope this does make sense. So, okay. I mean, the bottom line here is that when you multiply like bases, you add the exponents. Okay. Well, that's what multiplication. What about division? Well, that's what this example is illustrating for us. Suppose now we're assuming a is a non-zero real number. Okay, well, let's now consider this, a to the 7th divided by a cubed. Okay, well, if we expand the top and bottom, right, we have 7 copies of a. Here we have 3 copies of a. So let's, but notice there's going to be some cancellation. A is not 0 here. Well, if we cancel, 1, right, this one cancels, like so. We have 4 copies of a left over after cancellation. So we get 8, so we have 4 copies of a. This is, of course, a to the 4th. And 4 we know is 7 minus 3. So what am I illustrating here? Well, if a is any non-zero real number, m and n are integers, when you divide like bases, you subtract the exponents. So when you divide like bases, you subtract the exponents. And that's also the example illustrating here, 5 to the 6th over 5 squared. That's 5 to the 4th. Again, you subtract the exponents. So it's just another exponent rule, so to say. Are there any questions about this? Okay, well, here's another. So this, I said I would go through why this is true, why a to the 0 is 1 if a is not 0, for any a not 0. So here I'm just giving an outline of a proof. Let's suppose a is not 0. So we're going to assume that. Well, then if you do a divided by a, you're going to get 1. So 1 is equal to a divided by a. And this makes sense because a is not 0, right? 0 over 0 is not defined. But also by our exponent definition, a to the 1 is equal to a. Remember, if the exponent is 1, we don't have to write it. So a is really the same, a to the 1 is the same thing as a. So using this, we get 1, and this, we get 1 is a to the first over a to the first. Okay, how does that help us? Well, going back to this rule, you divide like bases, subtract the exponents. This becomes a to the 1 minus 1, which is a to the 0. So 1 we get is a to the 0, which is the same thing as writing a to the 0 is 1. I thought it was cool to give a little proof like this. Now you see why this is true. And we did use the fact that a is not 0, right? Because otherwise a over a would not make sense. So, oh, did I press it too much? No, we're good. Okay.